Good morning. Good morning.
Good morning, sir.
Good morning, sir.
Morning. Engineer Ibrahim, good morning. Oh, you are muted if you are talking.
Good morning, sir. How's the weekend, sir?
Good, we thank God. So, good morning to everybody. Um, you're all welcome to this first lecture. Our plan is to be having these lectures till we get to the point of being able to carry out reservoir simulation. So, I won't take much of our time. I'll just allow Engineer Ibrahim
Okay.
just so that we don't
It's 9 o'clock, so I believe we can start. Um, main reason why we have to start by understanding the fundamentals of reservoir fluid behavior and how it's being analyzed in the lab is because without understanding what's happening in the lab and the basic concepts, if we just jump into the PVT modeling and the software, some people might be left lost. So I hope this will be very important and help us to move fast. So understanding and characterizing reservoir fluid is essential for optimizing reservoir management, designing production strategies, and ensuring efficient hydrocarbon recovery. And the main objective of this lecture is to learn the fundamentals of reservoir fluids, understand the behavior of hydrocarbon mixtures, explore the role of pressure or the impact of pressure and temperature and how phases of this fluid changes. Also to classify the reservoirs and the possible reservoir fluids in each of the types of reservoirs based on the fluid and also the types of phases being exhibited by them with respective impacts of pressure and temperature. Also, we'd like to analyze and understand the pressure temperature diagram and discuss oil and gas reservoirs, be able to identify types of fluids present in these reservoirs, and also understand the laboratory analysis being done on these reservoir fluid samples. So reservoir fluids are naturally occurring mixtures, usually hydrocarbons and some non-hydrocarbon mixtures, which we call impurities, some of which are nitrogen, carbon dioxide, and H2S. They are also usually found within the reservoir pore spaces, existing in liquid and also gaseous states, sometimes supercritical states, depending on pressure and temperature conditions. These fluids can be classified based on the phase behavior, and we can classify them in 5 different types: black oil, volatile oil, dry gas, wet gas, and retrograde gas condensate. Each of these fluids exhibit distinct PVT characteristics. So with the help of PT diagram, we will discretize all of them. And we'll also try to understand the PVT properties: the bubble point pressure, the dew point pressure, the gas oil ratio, the formation volume factor, the oil density, viscosity, and so on, because they're all critical for reservoir engineering applications. We characterize fluids so as to, for we reservoir engineers, it helps us characterize the fluid, which helps us in integrating a model to mimic the reservoir and the fluids within the reservoir so as to optimize production strategies and predict future performance of a reservoir. But it's not only limited to us, it's been applied to other disciplines also, such as facility people, process engineering people, production technology people, and so on. So PVT properties are fundamental for reservoir characterization, fluid analysis, production forecasting, and reservoir simulation, enabling engineers to make informed decisions regarding reservoir development and production optimization. As oil and gas is produced from the reservoir, they are subjected to series of changes, more of pressure changes, though we usually assume isothermal temperature, which all leads to compositional changes of these fluids. Such changes affect transportation behavior, volumetric, and it makes impact actually to the volumetric and transport behavior of these reservoir fluids and consequently the produced oil and gas volumes. So types of reservoir fluids determines depletion and production strategies and also how we design our facilities, surface facilities. So this is a PT diagram on the y-axis. It's usually our pressure in PSI, and the x-axis is our temperature in degrees Fahrenheit. So reservoirs are broadly classified as oil or gas reservoirs. And these broad classifications are subdivided based on initial pressure and temperature, composition of the reservoir, also surface conditions. Let me do some graphical illustrations, please. And let's say this is our PT diagram. This is the phase envelope, on which within this phase within this place we have the two-phase region, and can you see my screen?
Yes, we can.
We have a critical point here.
Yes, sir.
So from this point, let's say this is A, this is B, this is C. From this, the curve from this point to this point is my dew point curve, bubble point curve.
Points.
This is the critical point. From the critical point to this point is the dew point curve. The bubble point curve is a curve where first bubble of gas evolves, while the dew point curve is the curve where the first droplet of condensate drops out of the gaseous phase. So I'm trying to classify the reservoir We can classify it with respect to temperature, so if this is my critical temperature, all reservoirs that have temperature above this critical temperature are regarded as gas reservoirs. All reservoirs with temperatures below this critical temperature, which happen to fall within this area, are regarded as oil reservoirs. And also with respect to pressure, we can also classify reservoirs with regards to their initial pressure in relationship with the bubble point pressure. So let's assume a pressure decline curve. For example, let's say this is our pressure decline curve. If this point is our initial reservoir pressure, and this point is the curve at which we call the bubble point curve. If this is the point where our pressure touches the bubble point curve, that will be our corresponding bubble point pressure for this reservoir that passes along this path. So if the initial reservoir pressure is higher than the bubble point pressure, that reservoir is regarded as an undersaturated reservoir. All gas remains dissolved in the oil phase until it reaches this bubble point curve. So as pressure depletes, gas expands within the oil column, but it will not start liberating, or it will not start leaving the oil column until it reaches the bubble point curve. So as pressure continues to deplete below the bubble point curve, as I told you earlier, anything within this phase envelope is a two-phase region. So anything below this bubble point pressure, as the pressure depletes below this bubble point pressure, we will be experiencing two-phase within that reservoir, thereby having the oil and the gas within the reservoir. And the surface condition for this reservoir usually is within the two-phase envelope, which means at the surface, we should be expecting gas and oil. We also have a type of reservoir with respect to pressure, whereby we call it saturated reservoir. If the initial reservoir pressure is below the saturation curve or saturation pressure, let's say the reservoir pressure decline path Hello, can you hear me now?
Yes, you
Yes,
can
sir.
hear. I think you were muted
Sorry,
before.
that was my mistake. So saturated reservoirs, we classified reservoirs based on temperature, and we're trying to classify the types of oil reservoirs based on pressure. So we also have a saturated reservoir which is a reservoir that has an initial reservoir pressure below the bubble point pressure. And in this scenario, we are already within the two-phase envelope, and we also have reservoir that is also called free gas cap reservoir, whereby the initial reservoir pressure is equal to the bubble point pressure. And I believe you guys have read all this previous
Yes.
assignment that I gave you guys. So because of time, I think doing the graphical illustrations might take a lot of time. So let me speed up and go back to the slides. So the reservoirs can produce different types of fluids, such as black oil, volatile, gas condensate, wet gas, and dry gas. And I would like to hear your own understanding. Who can explain black oil for us, please, quickly?
Okay. One is I can explain that.
Okay, Emmanuel, carry on.
Yes. Okay, so from my understanding, black oils, the reservoir pressure is above the bubble point for such kinds of reservoirs. So it's actually undersaturated with the gas still being dissolved within the oil. As pressure drops below the bubble point, it goes into um, a two-phase state where you have gas and liquid. And even eventually, when the pressure drops, as um, the fluids go up to the separator, it's still within the two-phase. And then what's special about black oil reservoirs is the spacing between the lines. The spacing between the quality lines is almost equal. So the oil shrinkage is not as much, maybe compared to like condensate reservoirs. Also, yes, the reservoir temperature is tends to be lower than that of the critical point, than the critical temperature. So it passes through the bubble point section of the PT diagram. That's just a brief explanation from my understanding.
That's good.
Thank
Um, I think you're trying to mix things up. Actually asked you to explain black oil. Yeah, you did that, but you went ahead to start explaining undersaturated reservoir. That's more like you trying to explain the type of reservoir. And I think I've done that earlier. You can classify reservoir with respect to temperature, and you can classify reservoir with respect to pressure. So black oil
you.
reservoirs are usually reservoirs that exhibit um, moderate pressure, moderate temperature and pressure, really a bit far away from the critical point, and they exhibit a formation volume factor within the range of 1.1 to 2.0, approximately reservoir barrel per STB. This kind of fluid usually have an API gravity range within 10 degrees to 25 degrees, more to say heavy to medium crude. And it appears dark, and it's usually called heavy or moderate heavy. It produces small amount of gas upon reaching the surface because it has small amount of gas being dissolved within it. And as I said earlier, it's found in low temperature and low pressure reservoirs, which is around this area of the phase PT diagram. Also, there is a volatile oil, which is not far away from the critical point. or closer to the critical point, though some literatures will discretize this into 5 types within the oil reservoir region. You might say far critical, black oil, then volatile oil, then near critical. Some of them will say low shrinkage, but I believe low shrinkage, near critical, and volatile can fall within the volatile context. And the far critical or low shrinkage oil can fall within the black oil. So it all depends on the literature you refer to. Volatile oil usually ranges between 26 degrees API gravity to around 45 degrees, and usually called the light crude. Its formation volume factor ranges between 1.2 reservoir barrel per stock tank barrel to 2.5, and it has an intermediate gas oil ratio, not like that of black oil. Black oil is usually within 150 to like 800, but the volatile oil is usually 1,000 and above, like 1,000 to 2,000 approximately, scuffed by STB. It contains a significant amount of intermediate hydrocarbons, C2 to C6, produces large gas volume compared to black oil at the surface, and the reservoir conditions are usually moderate pressure and moderate temperature, not like the black oil that has low pressure and low temperature. There's also the retrograde gas condensate, which exhibits a special behavior. Unfortunately, from the initial reservoir pressure, which is this, let's assume this is our initial reservoir pressure of the retrograde gas condensate. As pressure starts to deplete, it goes down. Upon hitting the dew point curve, the first droplet of condensate starts to drop out, and it falls within the retrograde region. This is our retrograde region. And what happens within this retrograde region is that it exhibits a special anomaly whereby within this region, upon crossing the dew point curve, it starts dropping condensates. As pressure continues to deplete, downwards within the pressure part through the retrograde condensate, it will continue condensing liquids, but upon reaching this point whereby it will leave the retrograde region, it will start reversing back to its gaseous state. That's the difference with this other kind of fluids. So it exhibits a behavior whereby as pressure depletes from initial reservoir pressure, upon reaching the dew point curve or the dew point pressure, we start dropping liquids, which we call condensates. To continue dropping that condensate liquids so far as the pressure continues to deplete within the retrograde region, but upon exceeding the retrograde region as pressure depletes, what happens again? It starts reversing back to its gaseous state. Then there's the other kind of fluid, which is also within the gas reservoir region. It's called wet gas, usually closer to the creek condensate term. This is the wet gas region, and we also have the dry gas, which is far away from the creek condensate term and the phase envelope. But the special thing about the wet gas is that, yeah, it will not fall within the two-phase region. It will not, it doesn't exhibit two-phase behavior within the reservoir, but unfortunately, its own separator condition, it's within the two-phase region, which means at the surface, it will produce some amount of liquid. That's why it's called wet gas. And the black oil, the volatile oil, all have their separator condition within the two-phase envelope, which means at the surface they will be producing two phases. The wet gas also produces two phases because its separator condition is within the two-phase envelope. But the dry gas, which is this, and it's far away from the cricondentan, far away from the phase envelope, has its own separator condition outside the two-phase envelope. Thereby, it will have dry gas within the reservoir and produce dry gas at the surface. So the wet gas, not typically measured with regards to the API gravity, but contains some heavier hydrocarbons ranging from C2 to C4. That's why it exhibits a bit of liquid production at the surface. Predominantly methane with small amounts of heavy hydrocarbons, as I said earlier. So it also exhibits a GOR higher than 50,000 scuff per STB. But the dry gas over here, not typically also applicable to API gravity calculation or measurement. It consists entirely of methane, and it exhibits a formation volume factor ranging from 0.002 to 0.004 reservoir barrel per SCF. Mostly pure methane, exists as gas both in the reservoir and at the surface. So we have basically discussed all this using those graphical illustrations. Key properties being measured or key properties being considered for this PVT analysis are bubble point pressure, dew point pressure, which I've also discussed that. Is the fluid compressibility, formation volume factor, fluid compressibility. The fluid compressibility is the change in volume of the fluid with respect to the change in pressure. It quantifies how the volume of the fluid changes in response to changes in pressure, thereby affecting the reservoir behavior and fluid flow. Formation volume factor is more of a shrinkage factor. It accounts the expansion or contraction of the oil volume due to changes in pressure and temperature. Usually the volume within the reservoir is not the same volume you will get at the surface due to gas libration. The gas oil ratio, which is the ratio of the volume of gas produced to the volume of the oil produced at thermal condition. The viscosity also is a key property, which is the resistance to flow, and the density, which is the mass per unit volume of the fluid. It influences the fluid behavior, pressure calculations, and buoyancy effects in the reservoir. So we'd like to discuss some laboratory analysis of the reservoir fluids. And I believe you guys have read some things about it. I have a question for you guys.
Yes, sir.
Who can list out the experiments, the laboratory experiments that are usually done on the reservoir fluid samples?
So is it like checking their composition, like to know the components of the fluids of
Mr.
maybe the
Pius
amount of.
or Nora? Hello, Mr. Pius.
Yes, sir.
Can you answer the
Yes,
question?
sir. Good morning, sir.
We want this session to be very interactive. You guys have been silent, so I want you to answer the question.
Okay, sir. Uh, that's the test for the fluid in the reservoir.
You said what?
Sir, is it the test to determine the composition of the fluid in the reservoir?
I said, can you list the experiments that are being done in the laboratory on the reservoir fluid samples?
Okay. Maybe like the wettability test, like that.
The what?
Uh, Maybe wettability test.
For PVT analysis?
Okay, for PBT, for
We're
PBT.
discussing PVT now.
Okay, sir. I think like this a slim tube test. Hello, sir. Good
It's
morning, sir.
also a type of experiment, but extended fluid test experiment.
Okay.
What
Hello.
I'm expecting from you guys is the first thing you do when you collect
So, Mohammed,
lab
Mohammed,
composition analysis.
Mohammed.
Yeah.
Sorry, let me come in.
Hello, sir.
So,
Hello, sir.
Dimeji, let me hear what you're going to
Sir.
say
Yes, sir.
first. Can you answer the question?
Okay, we have the density. Yeah, the density test. We run it.
Okay, Sunday
Hello,
is raising
sir.
up his hand.
Either Sunday, can you
Yes, good morning, sirs. We have the constant composition test, CCE, and the differential liberation test.
Is that all?
Which other one? Hello, Sunday, are you still there? Hello.
Oh, yes, sir. Yes, sir.
So is that all?
No, but this is just the one of the basic test lab tests we take for PVT analysis, the constant composition test, and then the differential liberation, stage separator test.
Yeah, thank you for that effort. That's a nice one. We have the we have the composition analysis, which is the first thing that has been done in the lab to actually determine the composition of the fluid, including the hydrocarbons and impurities. You want to know what are the constituents within the fluid sample. And there is also the constant composition expansion test, which determines the bubble point compressibility and the fluid shrinkage. And there's also the differential liberation experiment, DLE, which simulates reservoir depletion to determine the GOR, the oil shrinkage, and oil density, and so on. We also have the separator test, as you said, which simulates or try to analyze how the surface separation into oil and gas phases so as to design an optimal surface facilities. There's also the viscosity tests or viscosity measurements, which has been done to measure the resistance to flow of the fluid at varying pressure steps or varying conditions. The composition analysis is done using a chromatography machine. And let's take it step by step. The objective of the PVT laboratory analysis is to understand the importance of laboratory studies so as to characterize the reservoir fluids and evaluate that will help us to do volumetric analysis and future reservoir management and studies. The key points are the purpose of the laboratory analysis, which is accurate characterization of the reservoir fluid, assessment of volumetric behavior under varying pressure, temperature, conditions, types. We have two main types of laboratory tests, the primary test and the routine laboratory test. The primary test, which is done on site, That's upon completing the exploratory well, when they collect the samples, they do some tests on site, on the well site. Then there's also the routine laboratory test. After collecting the sample from the well, we carefully transport it to the lab to take a routine laboratory test. And the primary test is usually done to do some key measurements, which include specific gravity, the GOR. Importance is to provide a quick and cost-effective assessments of reservoir fluids. For the routine laboratory tests, we have 6 experiments, or let me say 5. It depends on the type of fluid. If it's oil, do composition analysis, constant composition expansion, differential libration experiments, separator test, and viscosity tests. For gas samples, we do composition analysis, constant composition expansion tests, differential libration expansion tests, separated tests, but we will not do constant volume depletion. Okay, for gas, we do constant volume depletion, while for oil, we do differential libration experiment and viscosity test for all. So 5 for each. For oil, we do differential libration experiment, not CVD.